Okay, so I have uploaded the note related to rectification in the group. I will go through it quickly. What we do in rectification is we convert AC signal into DC, AC current into DC current. Okay, and here we use diodes to rectify AC signal into DC signal. We know that AC signal will have a positive signal and a negative signal that alternates. So we can convert this into DC signal where the current is always in one side. It doesn't alternate with time. So in a direction. So there are two types of rectification: half wave rectification and full wave rectification. Let's check half wave rectification. So in half wave rectification, we have a very simple setup. Diode, and then a resistor, load resistor, and the input. We know that the input is going to have a sinusoidal signal which will alternate with time in the positive and the negative direction. So here, when the positive half cycle is now the input, let's say the direction of current in this direction. Therefore, the diode is forward biased, thus the current will flow in this circuit. And here we can observe a potential difference across this. So our output will be, for the positive half, you get the positive half here. When it comes to this negative half, during the negative half, the current will try to flow in the opposite direction. The current will try to flow in the opposite direction, that is in this direction. So the diode becomes reverse biased. The diode becomes reverse biased. If it is reverse biased, there is no current flow. Current cannot flow. I is equal to 0. Then there is no potential difference. Then this negative half of the cycle is not available in the output. Again, for the positive half, you get the output. From this complete wave, only half of the wave is being rectified. The other half is not used. So here we call this one as half wave rectification. For this DC signal, we get a value that is varies from 0 to a maximum value, and then there is no current for a certain period of time. Again, we get the next half cycle. To overcome this, we can use a large capacitor. A large capacitor across this resistor. When we use a large capacitor, when there is a current flow, in this direction, when there's a current flow in this direction, this plate gets positively charged and we will have a current flow downward. When there's a current flow downward. At the same time, this capacitor gets charged. And for the negative half cycle, during the negative half cycle, there is no current in the circuit. In this direction, current cannot flow, right? There is no current in the circuit, but this capacitor has saved some charge, and this plate is positive. So the current will flow from the positive plate to the negative plate through this resistor, which will be in the downward direction. So can you remember when there was a forward bias, when this diode was forward biased, this was the direction of current. When the capacitor discharges, again the current is in the same direction. So during this period where the value tries to become zero, because we have a capacitor now, there's a current flow. Now this value doesn't become zero. Instead, from the maximum, when the current is when this value is starting to reduce, charge will flow out of this capacitor, okay, maintaining the current in the circuit. So we call this one as smoothing. Call this method as smoothing. So during smoothing, the current doesn't go to zero initially, but it's starting from zero, right? This graph is starting from zero. Why is that? It is starting from zero, and then you get the graph like this. So the reason is, initially the capacitor was not charged. Initially the capacitor was not charged, so it's zero, and with time it charges, and after that it is not having enough time to completely discharge. It doesn't have enough time to completely discharge. That is why it's varying like this. Okay. So next, that's the idea of half-wave rectification. And under the note, there we have mentioned two note. So one of the note is about smoothing, I explained. And the second one, they are talking about maximum reverse voltage, right? Maximum reverse voltage. That is the peak inverse voltage. So what is this peak inverse voltage? When we apply a AC signal, the voltage, I'm talking about the applied signal, okay? It's varying from positive to negative side. And this maximum voltage, this voltage, that is the maximum reverse voltage. Okay, that is the maximum reverse voltage. Now, what do you think about this negative half cycle? This negative half cycle act as reverse voltage, act as reverse voltage for this diode. It is acting as the reverse voltage for the diode. But in the diode, can you remember, when we apply a reverse voltage, there won't be any current, but suddenly the current start to increase. The current start to rapidly increase, just like this, no current at all, and then increase. So this is the breakdown voltage. You know, remember we talked about breakdown voltage. When breakdown voltage occurs, we cannot use that resistor anymore. Use that diode anymore. So what is this peak inverse voltage? Peak inverse voltage is a safety measurement, safety voltage that is slightly less than the breakdown voltage. So this is peak inverse voltage. So it is just in front of, not just, it is by a huge amount, it is before the breakdown voltage. So we avoid applying voltage greater than this, okay, so that the diode won't go into a breakdown. So that is the peak inverse voltage. So soon as the voltage we apply exceeds peak inverse voltage, the diode doesn't get damaged, but there is a chance of damaging the diode if we use it above peak inverse voltage. Okay, is the difference between breakdown voltage and peak inverse voltage, clear? Do you get the idea of breakdown voltage and peak inverse voltage? If you have some space, put a small graph beside that and leave I versus V. So this is the mark this one as the breakdown voltage, and in front of that peak inverse voltage. Mark these two. I hope that's some space. Next, let's talk about full wave rectification. In full wave rectification, we are utilizing this negative half cycle also. In full wave rectification, we have two methods. One of the method is center tap method. The other one is bridge circuit. So let's look at the center tap method. In the center tap method, we have two diodes. So this is a transformer. In the transformer, we have in this coil, in the secondary coil, we have tapped the center to the output. Okay, and on the other two ends, we have two diodes connected. When current is induced in the secondary coil, when the current is induced in the secondary coil, let's say the current is induced in the downward direction. If the current is induced in the downward direction, now current when induced in the downward direction, this diode gets forward biased. This is forward biased, so current will flow through this, and through this resistor, the current flows down and returns back to this point. If the current is induced in the upward direction, it goes, this diode gets forward biased, current flow through this downwards, and through this wire again it returns. So this center acts as a negative. It doesn't matter whether the current is induced in the upward or the downward direction. For both the cases, the current through this resistor is always downwards. Therefore, if we have an input, a sinusoidal input, the output the output across this resistor will be like this. We have a smoothing capacitor, therefore it doesn't let the output current reach to zero. It will maintain at a certain level. So this will be the final output. Now, why do we have negative and positive sign here when the current is flowing in this direction? Can you remember when current is induced in a rod? Current is induced in a rod. If current is flowing in this direction, this is minus and this is plus. For the external circuit only, current flows from plus to minus, but in the induced rod, the current will flow from negative to plus. Okay. Do you have any doubt with center tap method? Next, we have the bridge circuit. The easiest way to draw the bridge circuit is to draw uh, the parallel diodes in the same direction. That is how you can remember them easily. The parallel diode are in the same direction. And we get the output from this and this in the opposite directions. Okay, we get the outputs from the opposite nodes. So these two will be the output. And we give the input signal to these nodes. This is where we supply the input. Let's say the here we have the load resistor and the resistor, the capacitor for smoothing. Now the signal, let's say we have a positive signal. We are talking about this positive half. Okay, during the positive half, the current is flowing in the upward direction. The current is flowing in this direction. So this diode is anyways reverse bias. This is forward bias. Therefore, the current will flow through this, and through this resistor it goes down. And when it comes to this point, this point, let's say this is diode D1 and this is diode D2. The current will flow through D1. Okay, the current will flow through D1 and it comes out of this circuit. It comes out of this bridge. Now, my question, the current could have gone through D1, right? The current could have gone through D1, but it didn't. What might be the reason? What do you think about D1? Is D1 forward biased or reverse biased? Is it forward biased or reverse biased? At a glance, it seems as if it is forward biased, right? When we look, it looks as if it is forward biased. But let's think about the potentials. The current started flowing from here. So I'll take this voltage to be positive. Let's say I'll take some value so it will be easy for you. Let's say it was at around 10 volt. So along this, it might have dropped several times, and here the voltage is 0.7, because soon after this it becomes 0. Now, what can you tell about this diode D1? Is it reverse biased or forward biased? Is this reverse biased or forward biased? It is actually reverse biased, because on the cathode side the potential is high and on the anode side the potential is low. Therefore, it is reverse biased. That is why the current didn't flow through this. Okay. Next, let's uh, find out about the next half. For the negative half, the current will flow in the opposite direction. So it is flowing in this direction. Now, diode D2 is anyhow reverse biased. The current goes through this diode. And from here, through this resistor, it goes down, comes to this point, and again D2 is reverse biased, and this is forward biased. When it comes to this point, D2 is reversed. Yeah, okay. So now it goes through this and now it will come out. Is it clear how the current flows here? So for both positive and negative signal, the current is always flowing down. Therefore, we get a graph like this, but we have used a smoothing capacitor, so the graph will look like, okay, is the idea clear about the bridge circuit? Shahama? So when we use very high capacitance, this ripple, we call this one as ripple. Ripple is not that much observable. Okay, it seems as if it is almost constant. But to get a better value, I mean a better constant value, we can use a Zener. We can use a Zener diode. So the Zener is connected this way. We have the bridge. So this is the bridge circuit. And now we are going to get the output. We have the smoothing capacitor. And then we have the Zener resistor. And then the Zener diode. And the load resistor. Now, if our maximum voltage, is above, okay, if our maximum voltage is above our Zener voltage, let's say this is Vm. If Vm is greater than Vz, that means the Zener gets activated. So if the Zener gets activated, the potential difference across the Zener will remain a constant. That is at V. So the potential difference across this will remain at V. Okay. So this will be the plug. Initially it won't be at V. Why do we need this? Why do we need this Zener resistor? That is for, let's say our maximum voltage is 12 volt and our Zener voltage is 10 volts. So across this resistor, across this Zener, we get 10 volt difference. The remaining 2 volt will drop across this Zener resistor. If this Zener resistor is not present, then there is no possibility for 12 volt to drop. I mean, if there is 12 volts, all the 12 volt has to drop across RL. There is no any other option. So the circuit might not be working properly, or it might not work as we expected without this resistor. Okay, this resistor is important. Is the idea clear? So that is all about rectification. As I sent you the note before, I'm not taking any more time. Let's start transistors. Shaham, if you haven't copied, leave some space. Have you copied, Shahama? Okay. So next topic is transistors. We can classify transistor into two types: BJT, bipolar junction transistor, and second one FET, field effect transistor. Field effect transistor. So first, let's discuss about BJT. BJT. We can classify BJT into two types. BJT is classified as first NPN transistor or NPN transistor, and second PNP transistor. BJT is classified as NPN transistor and PNP transistor. In our syllabus, we will be talking about NPN transistor only, and PNP will be the opposite of NPN. So the PNP transistor, the NPN transistor, we have N region P region and N region. So here there are free electrons. Majority carrier is free electron, and in this region the majority carrier is holes, and here it's free electrons. And they have 3 pins. And we can show this one NPN transistor in a diagram like this. The direction of arrow shows whether it's PNP or NPN. So this arrow direction is from P to N. Using that, you can find whether it's a NPN or PNP transistor. So this is NPN transistor. So PNP transistor, we have the opposite. PNP. So this is P region, this is N region, and this is P region. Holes, free electrons, and hole. Here the direction of arrow changes. The direction of arrow changes. So as I mentioned earlier, you will have to mark using the direction of arrow. So always it is from P to N. Always it is from P to N. So this is P, this is N, and this is P. So this is PNP. This will be the symbol for PNP transistor. First point, BJT is an electronic device, electronic device with 3 regions and 2 PN junction. So in a junction diode, we only had 1 PN junction. Here we have 2 PN junctions. The regions are base, collector, and emitter. Base, collector, and emitter. So we can classify BJT as NP and PNP based on its construction. Based on the construction, BJT is classified as NPN and PNP. So these three regions are doped, but their level of doping is different. The base region, the base region is lightly doped, is lightly doped, comma, the the emitter region is is heavily doped, and the collector region is doped intermediately, is doped intermediately. So if we arrange the level of doping, Ne is doped heavily, next Nc, next Nb. N is the level of doping, where N is the level of doping. Okay. Once you have noted, let me know.